Is my screen visible?
Yes, sir.
All right. So we'll start now. So we'll continue with the earlier topic, that is the Rayleigh Ritz method. Okay. So in the previous class, we have started the beam problems. So we'll continue the beam problem. This time, if you remember in the last class, that is in the previous class, we have gone for the cantilever beam, and today we will see the simply supported beam. Okay, so let me draw a beam for you. So we have, let us say, simply supported beam, which is, let us say, like this. Okay, and we have support. Let us say this is your hinge support over here, and this is a roller support over here. Okay, and on this beam there is a load which is acting like this. Okay, so let us assume the length of the beam as, let us say, 5 meters. Okay, so this is distance from this point to this point is, let us say, 5 meters over here. Okay, and if the load is acting at the center, so of course the span which is over here, so this will be something like 2.5 meters. Okay, so this distance will be 2.5 meters. Okay, now the load value is also given to you. So this load value is 10 kilonewtons, which is acting at the center. Now for this problem, the value of E is also given to you. Okay, and the value of I is also given to you. So the value of E, which is given to you, is something like 2, okay, 2 into 10 to the power 5. This is newtons per meter square, and the value of I, that is moment of inertia, this is given to you as 4 into 10 to the power 6. This is millimeter to the power 4. Okay, so this is given in newtons meters, and here it is given in millimeter to the power 4. Okay, so we can rewrite these values with the common units. So what we will do, we will go for the units of force as, let us say, kilonewtons, and the unit of distance as, let us say, meters. Okay, so if I convert this 2 into 10 to the power 5 newtons per meter square into kilonewtons, okay, so this will come something like 2. Okay, I think I have made some mistake over here. Okay, let me rewrite these values. Okay, so this is already given in kilonewtons. Okay, so this is 8 and this is already in kilonewtons. So this is 2 into 10 to the power 8. This will be kilonewtons per meter square. This is already given over here. And if you rewrite this in meter square, a meter to the power 4, so this will be 4 into 10 to the power minus 6. This will be meter to the power 4 now. Okay, remember in the case of beam, we require a value of EI divided by 2. This is mandatory. Okay, so we can substitute these values. So this is 2 into 10 to the power 8. So this is the value of E, and I value is 4 into 10 to the power minus 6 whole divided by 2. So if you solve this, this thing will get cancelled, and as a result of this, what you are going to get is 400, and this will be something like kilonewton and meter to the power 2. Okay, so this is how the value of E will be, right? Now we have to start the solution of this problem, and if you remember, for solution we have to calculate the potential energy. Okay, so this total potential energy, that is denoted by a symbol, usually it is pi, and it is the summation of strain energy, that is U, plus the work done, that is the W. Okay, so for calculation of the strain energy, first thing what we have to do is we have to assume the function or the polynomial for the displacement. Okay, so now here in this particular case, what I'm going to assume, that this is my origin. Okay, so this will be my origin, and along this side you have the positive x-axis, and in the downward direction I'll be assuming the direction that is the positive direction of the deformation. Okay, so now with this assumption, now we have to assume the displacement polynomial. Okay, so here I'm going to assume a displacement polynomial, something like this. So here I will say assume the displacement polynomial. Generally it is denoted by a small w over here. So this I am assuming this as a0 plus a1 into x plus a2 into x square plus I'm going to write a3 into the x to the power 3. Okay, so this is what is I am assuming over here. Okay, so now since this is assumed, so we don't know the values of say a0, a1, a2 and a3. All these values now you have to find out. Okay, so for that particular purpose, first of all you need to draw the free body diagram of the given problem, and then you have to apply the boundary conditions. Okay, so now let me draw a free body diagram of the given problem. So let me draw a straight line. So this is a beam, so this is a free body diagram which I am drawing over here. Now what I am assuming over here, this is my origin. Okay, so at this origin your x will be called as x0. So I am calling this point as, let us say, x, this is, let us say, point number 0 for example. Okay, so this is point number 0. Okay, and here I am assuming one more point in between because the load is acting over here. So I'll call this as point number 1 and I'll call this as point number 2. Okay, so at with this assumption you can say the x value is 0 at over here, so this will be x0. Your x value over here will be called as x1 and its numerical value will be 2.5 meters, and here x value will be called as x2 and its numerical value will be 5 meters. Okay, now as far as the deformation is concerned, the deformation is there in the transverse direction, so this will be called as w. So the value of w will be called as w0 at this point and its numerical value will be 0. Why it should be 0? Because if you see at this joint there is a hinge support over here, and the property of the hinge support is that it does not allow the deformation in the vertical direction. Okay, so this is w0. Similarly here the w will be called as w1, and I don't know what is the value of w1. Okay, because load is there, so depending on the quantity of the load, the value of w is going to change. Okay, now as far as this part is concerned, so at point number 2 w will be called as w2 and its numerical value will be 0, because at this point, that is at the second point, roller support is there, and this roller support is not allowing the displacement in the vertical direction, that is in the w direction. Okay, so this is one boundary condition which is available over here. Okay, now there is another boundary condition which we can also utilize, that is the slope. Okay, now if you draw a simple deformed shape, okay, of this concentrated the beam which is subjected to concentrated load at the center. So if you draw the shape, your shape will look something like this, isn't it? And if you take a slope over here, so at this point there will be a rotation, let us say this will be, let us say, theta 0. Okay, and here also there will be a rotation, this value will be theta 2. But at this point, so at this point, so the rotation will be 0. Why? Because this is subjected to concentrated load, and under the load your rotation will be always 0. So here theta, so theta value will be called as theta 1 and its numerical value will be 0. Here the value of theta 0 will be unknown, and here the value of theta 2 will be also unknown. So now we have got three boundary conditions. One is at point 0 where the deformation is 0. The second is at point 2 where the deformation is 0, and third is at point 1 the rotation is 0. Okay, so the rotation means the angle, it is 0. So you can see at that point if you draw a tangent, it will be parallel to your x-axis. Okay, so now what you can do is you can make help of these three boundary conditions, and then you can have the elimination of the constants over here. Okay, so let us go one by one over here. So let me use the boundary conditions. So I'm just writing over here, that is applying boundary conditions. Okay, so the very first boundary condition which is available over here, that is at point 0. Okay, so at point 0 the value of x is x0, its numerical value is 0. Secondly, the value of w will be w0 and its numerical value will be also 0. Okay, and what we have assumed, we have assumed the value of w as a0 plus a1 into x plus a2 into x square plus a3 into x to the power 3. Okay, so this is what we have assumed, isn't it? So now with this assumption, let us apply the boundary conditions over here. So if you substitute at point this, so this value will be 0, this will be a0 plus a1, the x value will be 0, here a2, the x value will be 0, and your a3, the x value will be also 0. So if you solve this, what you are going to get is a0 value as 0. Okay, so this we have done plenty of times by now. So finally your unknown displacement polynomial w will be taking a shape of a1 into x plus a2 into x square plus a3 into x to the power 3. Okay, now let us apply the second boundary condition. Okay, so the second boundary condition, that is at point, I am going for point number 2. Okay, so point number 2 is this point. Okay, the other end, basically the roller support over here. Okay, so at this point number 2, what is going to happen? So x will be called as x2 and its numerical value will be 5, and your w will be called as w2 and its numerical value is 0. Okay, so this is what is the boundary condition. So now what we can do is we can rewrite this expression over here. So value of w is w2, its value is 0. So we can have a0, we can have a1, the value of x is nothing but 5. Okay, the value of a2, value of x is, let us say, 5 square, and this is a3 into 5 to the power 3. Okay, so this is how you can get the expression. So now what we can do is we can take this over here and we can divide the entire thing by 5. Okay, so if you divide the entire thing by 5, in that case you can get the value of a1 as minus, this will be 5 times a2 plus this will be 25 times a3. Okay, I think this should be negative, not positive. Okay, is it correct, everybody? Barabar hai hai?
Yes, sir.
Fine. So now we can express the value of a1 in terms of a2 and a3. Okay, so this is one expression we can obtain from this. So if you rewrite this value, so this value if you rewrite, so I'm talking about this value. Okay, so you have w equals to a1x. So this a1 now can be written as minus 5 times a2 minus 25 times a3 into x, okay, plus a2 into x square, okay, plus a3 into x to the power 3. So let us call this as expression number a. Okay, so this is one such expression by which you can get the value of displacement or the deformation of the beam. Okay, now we have one more expression or one more boundary condition is available with us, that is the slope. Okay, so first of all you need to find out the expression for the slope. So your slope, generally it is denoted by a symbol theta, and this will be calculated as dw by dx, isn't it? So dw by dx means you have to go for the derivative of this expression with respect to x. So if you do this, so for here this x will be gone. So what you are going to get is minus 5 times a2 minus 25 times a3. So this is first thing. Okay, plus, so this x square, so derivative will be 2 times x. So this will be 2 times a2 into x, and this will be 3 times a3 into x square. Okay, so this will be the expression for the slope. Okay, So let us write this as, let us say, B. So now you have two expressions, expression A and expression B. So A denotes the deformation and B denotes the rotation. Now we have one more boundary condition, okay? So that is at point 1, okay, not point 2, at point 1, okay? So I'm talking about the center point where the load is acting over here. So at this point the value of W is unknown, but the value of slope, that is theta, is known, okay? So here what I'm going to write over here is, here the X will be called as X1 and its numerical value will be 2.5 meters, and your theta value will be called as theta1 and its numerical value is 0, because this is a concentrated load acting at the center of the beam. So the slope at that under the load will be always 0, okay? So now you can use this boundary condition in the expression of theta over here. So your theta is already 0, so I'm writing down 0 over here. Now here everywhere I just have to just put the value of X as 2.5. so here I'm just going to write down minus 5 times A2 minus 25 times A3. Here minus, sorry, this will be plus 2 times A2 into this will be 2.5 plus 3 times A3 and this will be 2.5 whole square, okay? So here if you solve this particular expression, so if you solve this, so what you are going to get over here, this is minus 5 times A2, and if you go for this, so this will be 2.5 into 2, so again this will be 5 times A2. So this term itself is going to get cancelled over here, okay? And accordingly if you go for this equation, so this will be 0 and this will be minus 25 times A3 plus, so this will be 2.5 square. How much is that? Can someone tell me? 2.5 square, okay, into 3, okay? So this comes out to be something like 18.75 times A3, and if you solve this, so this will be minus 25. So even if you are able to solve this, this will be minus 6.25 times A3, but this is ultimately equals to 0. So this means what? Your A3 value is basically 0 over here, okay? Because A2 is getting cancelled, A3 is not getting cancelled, and it is equated to 0. So finally your value of A3 is becoming 0, okay? So now since the value of A3 is 0, what you can do is you can rewrite the expression A, which is for deformation, and expression B, which is for the rotation. So if you rewrite this expression, so your W now can be written as minus 5 times A2 plus here 25 times A3, okay? So 25 times A3, since the A3 is 0, so this term will not come into picture, okay? Then we have plus 2 times, sorry, my mistake, this has to be multiplied with X, isn't it? So this will be X, okay? So I'm talking about expression A, okay? So there is a X over here, isn't it? So this is X is there, then we have plus, this is A2 into X square, plus we have A3 into X to the power 3. Since A3 is 0, so it will be completely gone. Now similarly you can have the theta value, that is the rotation value. So if you go for, either you can go for derivative of this, or you can substitute the value of A3 as 0 in expression B. So in both the cases what you are going to get is minus 5 times A2 plus, here the other term will be gone, so here you will get something like 2 times A2 into X. Is it okay? Yes students, is it okay? Yes, somebody please respond.
Yes, sir.
Okay, fine, right? So let me slightly erase this, okay? Let me write down over here. So theta is dw by dx square, not x square, only x, okay? dw by dx, right? Now in case of calculation of the strain energy, we require d square w by dx square, isn't it? So we have to go for one more derivative of this. So we are going for d square w by dx square. So if you solve this, this term will be 0, and here what you are going to get is something like 2 times a2. Okay, so now let us do the calculation for the strain energy. Okay, so here the strain energy now can be which can be written as capital U over here. So this is something like EI divided by 2 integration over the length. We have d square w by dx square whole square into dx. Okay, so this is the basic expression for the value of strain energy. So if you remember the values, so EI divided by 2, earlier we have calculated at the beginning itself. So value of EI by 2 is 400, isn't it? So let me write down 400 over here. Okay, this will be integration over the length. So length is from 0 to 5 meters. Okay, and your d square w by dx square is nothing but 2 times a2, and this will be your dx. Okay, so if you go for the integration part, so this 2 will come out, so it will become 800 times a2 integration from 0 to 5, and this will be simply a dx. Okay, I think this is square term. Okay, so if this is square term, so this will be ये कितना हो जाएगा 8 into sorry, not this will be something different. Okay, ये कितना आएगा, somebody please tell me. So this is 2 square 4, 4 into 4, 1600, isn't it? Am I right? Yes, students, am I right?
Yes, sir.
बेटा बराबर है क्या, चेक करो. Yes, students, is it okay?
Yes, sir.
Yes.
Yes, sir.
Okay. So this is 1600 a2 square, and this will be dx will be simply x from 0 to 5. So 16 into 5. ये कितना आएगा 16 into 5? कितना आया? I think 8000.
Yes, sir. 8,000.
8000 a2 square. Okay, so this is the expression for the strain energy. Okay, I hope this is understood to everybody. Okay, now let us go for the work done. Okay, so right, for work done, we have a expression which is written as capital W, and we have the work done due to the point load, work done due to the surface load, and work done due to the volume load. Okay, so now in this particular case, the surface load is not there, volume load is not there, so only the point load is there, and it is written as the W at that point and the load at that particular point. Okay, so W is nothing but the vertical deformation at that particular point, and this will be P at that particular point. Okay, so right now if you see the problem, your load is acting at point number 1. Okay, so I am just rewriting this term as this is nothing but W at point number 1 multiplied by load at point number 1. Okay, so I need to first of all calculate what is the W at point number 1. So if you see earlier case, so your W value is minus 5 times a2x. Okay, so let me write down over here. So this is minus 5 times a2 into x plus a2 into x square. So this is the final expression for the value of W. Okay, so at point 1, okay, so let me write down over here, at point 1 the x value is nothing but 2.5. okay, so this is 2.5 meter. So this expression now can be written as W1 as this is minus 5 times a2 into 2.5, okay, plus a2 into 2.5 ka square. Okay, so finally you can get the value of W1. Okay, कितना आ रहा है W1? Anybody? Yes, please.
So minus 6.25 A2.
Sorry,
Minus 6.25 A2.
minus 6.25 times A2. Okay, so this is the value of W1. Okay, now let us substitute the value in the work done expression. Okay, so here this is our work done expression. Okay, so I am going to substitute these values over here. So your work done is nothing but minus W1 is minus 6.25 times A2 and load. So the value of load which is acting at that particular point is 10 kilonewtons, and the direction of that load is in the direction of the deformation. Okay, so here I am going to put this value as positive 10. Okay, so at the end what you are going to get the value of work done as something like 62.5 times A2. Is it okay everybody? यहाँ तक बराबर है?
Yes, sir.
Okay, so now let us quickly generate the total potential energy. Okay, so your total potential energy is nothing but strain energy plus work done. Okay, so let me go slightly over here. So your pi will be, okay, so if you refer the earlier portion, your total strain energy is 8000 into A2 square, isn't it? So this is something like 8000 into A2 square. Work done we have already taken care of this negative sign over here, so this is something like 62.5 times A2. Okay, so this is the expression for the total potential energy. Now in order to maintain the equilibrium, the total potential energy should be minimum. So in that particular case, this d pi by dA2 should be 0. Okay, so if you go for a derivative, so this will become 8000. Okay, this is 2 times A2. Okay, plus this is 62.5 into 1. Okay, so if you solve this, you should get the value of A2 as कितना आना चाहिए बताओ? Yes, somebody do the calculations please.
So minus 3.90 into 10 raised to power minus 3.
Yes, so this is minus 3.90625, okay, into 10 raised to power minus 3, right? So this will be the expression for or the value of unknown constant A2. Okay, now all the unknowns are now known. Your A1 is there in terms of A2. Okay, so you can see earlier we have calculated the value of A1. So here you can see A1 was in terms of A2 and A3. We have already found out the value of A3 is 0 over here. Okay, so your A1 is nothing but minus 5 times A2, isn't it? So your A1 is nothing but minus 5 times A2 plus, okay, A1 is minus 25 times A3 is also there. Okay, so this is minus 25 times A3. Okay, so out of which you see the A3 value is basically 0. So now can someone tell me what is the value of A1 now? So this is minus, this will be minus 5 times A2. So all you have to do is just multiply this value by 5.
So 0.0195.
0.0195. That's it, isn't it?
It's a positive value.
Positive. Okay. So
Suppose
because
minus
A2 value is negative, that's why this is coming out to be positive.
Yes, sir.
Barabar hai? Right. So now all you have to do is just substitute the values in the W. That is the expression for the deformation. So your A value you have already written in terms of expression 1, which is over here. So this is W is minus 5 A2 times X plus A2 times X square. Okay, so your W, this is ये कितना था? I forgot. That is minus 5 A2X. So this is minus minus 5, your A2 is minus 3.90625 into 10 to the power minus 3, this into x, okay, plus, okay, and your expression is A2 into x square, okay. So your A2 value is still same, so this is something like minus 3.90625 into 10 to the power minus 3 into x square, okay. So this is the expression for the deformation, okay. Now let us see how this deformation is there in the beam, okay. So since the value of W is now known, so now what I can do is I can simply go for the substitution of values over here, okay. So let me draw a simple beam which is over here, okay. So now at this point, okay, so I'm talking about this point over here. So at this point the value of x is 0, okay. So here in this expression, if you substitute the value of x as 0, what you are going to get, the value of W is 0. So here your deformation will be 0 at this particular point, okay. Now if you substitute here the value of x as L, okay, so where L value is basically your phi value, isn't it? So here if you substitute this value, say this x value is 5 now, okay. So can somebody do the calculation, and what is the value of W with the x value as 5?
सर 0
0 आ रहा है?
आना तो चाहिए, कैलकुलेट नहीं किया.
It should become 0 because यहाँ पर अपना क्या है, there is a support, so there should be a 0 value over here, okay. Now let us talk about the center point, okay. So let us talk about this point, okay. So I'm talking about the center point. So at this point the value of x is 2.5, right? So here all you have to do is just substitute the value of x as 2.5, and here also you just substitute the value of x as 2.5. So can somebody tell me how much is the value of W now?
So 0.0244.
Okay, so here you are getting a positive value, isn't it?
Yes, sir.
Positive value means downwards. So how much is that value? Once again,
0.0244.
this is in meters, okay. So you have now 3 different points, so all we have to do is join this line with the help of a dotted line, okay. So let me use this orange color over here. So all you are getting is a dotted line which is like this, okay. So this is nothing but the deformed shape of the beam, okay. And since this is a simply supported beam subjected to concentrated load, it should behave like this only, isn't it? So the maximum deformation will occur at the center of the beam, and its value is something like 0.0244 meters. So if you convert it into millimeters, so it will be something like 24.4 millimeters, isn't it? Have you understood this? Any questions as far as this part is concerned? Yes, students. ठीक है?
Yes, sir.
Okay. So I'm guessing there are no doubts now. So this completes one problem. Let us take a similar problem now with a different approach. Okay, so the same problem is there, but the approach which I'll be using over here, it will be something different. Okay, so let me push this slightly up. Okay, now let me draw the beam one more time. Okay, so let me draw this beam one more time. So this is my beam which is over here, and we have hinge support over here, okay, and we have a roller support over here, and at the center we have a load, okay, and the value of load is something like 10 kilonewton, and we already have calculated EI by 2 as 400. I think this is kilonewton meter to the power 2. Okay, so this we have already done, right? The distances are already known to you, but still let me draw. So the total distance of the beam is 5 meters and the load is acting at the center. So the distance will be something like 2.5 meters. Okay. Now, just pay attention now. If you observe the deformed shape, so your deformed shape should be like this, isn't it? So basically, you have the maximum deformation at the center and the zero deformation at the end of the beam. Okay. So if you observe very carefully, this is nothing but a sine curve, isn't it? So if you see the sine curve, so let me draw a simple sine curve for you. Okay. So this is my x and y axis over here. Okay, so this is x and y axis. Okay, and if you draw a sine curve, your sine curve is like this. Okay, let me use a red color over here. So your sine curve is like this. Okay, and then it is going down like this. Okay, so here if you put here, this is your angle. Okay, and here this is, let us say, angle, let us say alpha, and here you have, let us say, sine of alpha. Okay, so if your alpha value is 0, so you are getting sine value 0. If your alpha value is 180, then also your sine value is 0. But if your alpha angle is 90, in that particular case, this particular axis, okay, or this particular value which is there at the center, so this value will be the maximum and its numerical value is 1. Okay, so you see the sine curve and the expected deformation curve of the beam subjected to concentrated load at the center, it is exactly same. The direction may be reversed, but it is exactly same. So why every time I should assume the value of W as A0 plus A1 times x plus A2 times x square and plus A3 times x to the power 3, so on, so on. Why this? We can even go for a different function also. So this is something like where in place of a simple polynomial function, we can use a trigonometric function. Okay, so trigonometric function means in place of a1x and a2 and so on, so we can have the sine functions or maybe a cos function or maybe a different function. Okay, so what I can do is I can simply assume the value of W in form of a sine, that is, let us say, a into, I can say, the sine of pi into x divided by L. Okay, so this is, I'm assuming, in place of assuming this, I'm assuming this. Okay, why I'm assuming this, you just see. Okay, so in this expression, if you substitute the value of x as 0, what is going to happen? This entire term is going to become 0 because this x is 0. So this entire term is going to become 0, and what you are going to get is W value as 0. Am I right? बराबर बोल रहा हूँ? Students, please pay attention. Okay. Now, if I substitute the x value as, let us say, L value. Okay. So in place of using the x value as 0, okay. So what I can do is I can substitute the value of x as L. So if you substitute value of x as L, that this is, I'm talking about at this particular end. So in that particular case, what will happen? This L will be cancelled. So this L and this L will be cancelled. And what you are going to get is nothing but sine of pi. Okay. So sine of pi is nothing but sine of 180. And again, you will find the value of x at a distance L as 0. I'm not talking about 5 meters or 4 meters. I'm talking about length of the beam. Okay. And at the same time, if you substitute the value of x as L by 2, okay, L by 2 means what? At the center. Okay, so here earlier there was L over here. So here, if you substitute the value of x as L by 2, okay, that is L by 2. So what is going to happen? This L and this L will be cancelled, and it will have the value of sine of pi by 2. So sine of pi by 2 can be value, its value is basically 1. Okay, because at the center the value of this sine is always 1. So here, in place of writing x is equal to L by 2, so what W you are going to get? You are going to get this as 1. Okay, and of course you have a multiplication factor of a over here which will be unknown. So in place of assuming this big polynomial over here, you can simply assume a simple trigonometric function, maybe in terms of sine series, maybe in terms of cos series, and then you can go for the solution. Okay, so now let us try to find out the solution of the same problem using the trigonometric function. Okay, so here I'm going for the solution now. For the solution purpose, first thing what we have to do is we have to assume. Okay, so assume. So here what I'm going to assume, the value of w as the same one which just now I explained. So that is a into sine of, this is pi upon L into x. So this is I am assuming over here. Okay, so again if you go for the boundary condition, so let me draw a boundary condition diagram at the just next to this. So here I have x equal, so let us say this is point number 0, not point number 1. So this is point number 0, at the center this is point number 1, at the end this is point number 2. So here x will be called as x0, its numerical value will be 0. Here x will be called as x1, its numerical value is 2.5, and here x will be called as x2, its numerical value is 5. Similarly, here w will be called as w0, its numerical value is 0. Here w will be called as w1, its numerical value is unknown, and here w will be called as w2, its numerical value is 0. Okay, at the same time if you see the theta value, so theta will be called as theta 0. Here rotation will be there, so there will be a slope. Okay, and if you see this end also, this will be called as theta 2 and its value will be unknown. But at the center the theta will be called as theta 1 and its numerical value will be 0, because under the load there is a 0 slope. Okay, so now if you apply the boundary condition, okay, so if you apply the boundary condition over here, what you are going to get, you are not going to get anything, because you just see apply boundary conditions. Okay, so if you apply the boundary conditions in that particular case, what you are going to get, so if you apply over here, let us say at point 0, okay, not at point 1. So what you are going to get, w will be called as w0. Okay, your a, this will be sine, this is pi by L into x, so x value is 0. So ultimately what you are going to get, w0 as 0. So there is no point in applying this boundary condition, isn't it? Similarly, if you go for at point 2, so this will be w2. Okay, and this will be a into sine of, this is pi by L into x value will be L. So this will be get cancelled, and sine of pi is 0. So ultimately your w2 will be also 0. Okay, so there is no point in going for the applying the boundary conditions. Okay, but if you take this w value, okay, and if you go for a slope, so for slope, so theta can be calculated as dw by dx. So here can anybody tell me what will be the derivative of this theta? Batao. dw by dx, anybody? बताओ भाई. This is d by dx of a into sine of pi upon L into x. Yes, somebody please tell me what is this derivative? Boys, girls. अरे कोई तो बताओ, नहीं आता? Yes, students, anybody? Okay, so let me explain. So basically, while going for a derivative, you just have to refer your 12th standard notes, go for the some equations which you have studied earlier. So basically this theta value, if you go for a derivative, it will be something like pi by L. Okay, so x will be gone, then it will be multiplied by a into the derivative of sine, that is the second component. So this will become a cos of, this is pi by L into x. So this is the value of theta, that is the rotation equation. Okay, so now you can simply use this in the strain energy calculations. And if you remember, in the strain energy calculations, you need to have a value of d square w by dx square. Okay, so this is d square w by dx square. So all we have to do is just go for a derivative of this expression, that is the theta expression, one more time. Okay, so if you go for a derivative of this expression, this will be something like pi square divided by L square into A, and into it will be something like sine of pi upon L into X. So this is the expression for the strain energy which is required over here. Now let me calculate the strain energy. Okay, so your strain energy is usually written by a simple expression, that is,
Sir,
sorry.
so the value will be negative.
Yeah, the value should be negative. I totally agree. I think I have written wrongly over here. Okay, let me check. Sine का cos होगा ना, तो cos का minus sine होगा, बराबर. So this should be negative. Okay, so your strain energy, that is the pi, not the pi value, that is the u value. Okay, so this is u value. So u is basically E into I divided by 2 integration over the length, then d square w by dx square whole square into dx. Okay, so if you remember, your EI by 2 is nothing but your 400, and your length will be now from 0 to 5, and this will be something like minus of, this is pi square by L square into A into sine of, this is pi upon L into X. Okay, and this will be whole square. Okay, whole square into dx. Okay, so you can do the integration part later on. I already have the solution for this integration. So your u value, finally it will be something like pi, okay, to the power 4 आएगा. Then we have E, I think I have the values in terms of EI. Okay, तो EI ही रहने देते हैं इसको. So this will be pi to the power 4 EI divided by, this will be 500 into A2 square. Okay, so let us keep, in place of this 400, let us keep this in terms of EI only, EI by 2. Okay, so this is the expression for the strain energy. Okay, now coming to the work done part. Okay, so work done will be slightly different. Okay, because the equation is different. Okay, so work done, just now we have seen that the value of work done is having only one component, that is minus WP, that is the point load. So this will be load, the deformation at point number 1, and the load which is acting at point number 1. Okay, so so at point 1, so at point 1, what we have, W will be called as W1, so its value will be unknown to us, and your X value. Okay, so your X value is basically X1, and its numerical value is 2.5 meters. Okay, so let us quickly go through the W expression. So W expression is W equals to A into sine of pi by L into X. So this is what we have assumed. Okay, so your W is nothing but A into sine of, this is pi by L into X. Okay, so if you substitute the value of X as 2.5 and L value as 5, okay, so what you are going to get, you are going to get the sine of pi by 2, isn't it? So this sine of pi by 2 is nothing but your 90 degree, and it will be always 1. Okay, so let us substitute this. So your W will be A into this will be sine, this is pi, this will be 5, this is 2.5. Okay, so this and this, so this will be half over here, and ultimately what you are going to get, the value of deformation at that particular point. So this will be point number 1, isn't it? So this value is nothing but your A value. Okay, that is a constant value, right? So now if you go for the work done, okay, so this is your work done part. Okay, so work done is capital W. So this is minus of W1. So W1 value is nothing but A, and your P value is 10 kilonewton. Okay, because if you remember, the load which is acting at point number 1 is 10 kilonewton. So ultimately the work done value is nothing but something like minus time 10 times A. So this is the work done. So now let us go for the total potential energy pi, which is the sum of strain energy plus work done over here. So your strain energy just now we have calculated, it is pi to the power 4. This is nothing but EI divided by 500. This will be A square plus work done. So work done is nothing but minus. Okay, so this is minus 10 times A. So this is nothing but your value of pi. So you can see the value of pi is there in terms of A. So in order to maintain the equilibrium, your total potential energy should be 0. So for this purpose, d pi by dA should be equals to 0. So if you go for a derivative of this, so this will come outside. So pi to the power 4 EI divided by 500, and this will become 2 times A minus this will be 10. This will be equals to 0. So you can take this side over here and you can simply find out the value of A. Okay, so can anybody tell me what is the value of A, please? By substituting the value of EI. Okay, E और I पूरा ये करके बताओ A की वैल्यू कितनी आ रही है?
सर 0.0320
0.0320. Okay, so this is the value of A now. Okay, now what is the displacement polynomial W which we have assumed? It was A into sine of pi upon L into X. Okay, so now we know the value of A. So this displacement polynomial U now W can be now rewritten as 0.032 into sine of pi upon L into X. Okay, so this is the final answers. So now if you substitute the values, okay, so let us substitute the values. So let me draw one diagram which is over here. Okay, so at this point, so you have X value as 0, here you have X value as 5, and here you have X value as 2.5. Okay, so I'm talking about these 3 points over here. Okay, so we already know that if you substitute here the value of X as 0, so this entire term becomes 0, and you will get the value of W as 0. If you substitute the X value as L, okay, so I'm talking about this point over here, ye wale point pe. So if you substitute the value of X as L, then also this entire term is going to become 0. So this entire term will be 0, and you are going to get the deformation as 0. Okay, but if you substitute the value of X as 2.5, so I'm talking about the point which is over here. So in that case, your this value, that is X value, will become L by 2, and the sine value will become sine of pi by 2. Sine of pi by 2 is 1, and what you are going to get is only this constant. So at this particular point, you have a vertical deformation which is like this. Okay, so you have a vertical deformation like this, and its value will be 0.03 and 2, and the line should be drawn like this. Okay, so it's a sine curve, so you have to draw a sine curve which looks like this. Okay, so final answer, so the deformation at this point W will be something like 0.032 meters. So this can be rewritten as 32 millimeters. Okay, I hope this is clear to everybody. Is there any queries? Yes, students, are there any queries, please? No? No, fine. So just now we have seen 2 approaches to solve the problem. Earlier we have solved this problem using a displacement polynomial. Then displacement polynomial was like this, that is A0 plus A1x plus A2x square plus A3x cube. And with this polynomial, if you find out the solution, so maximum deformation was coming at the center, and its numerical value was something like 24 millimeters, isn't it? But if you use the same, if you solve the same problem using the trigonometric function, that is the sine curve, you are getting a different answer. So this different answer is nothing but 32 millimeters. Okay, so earlier it was 24 and now it is 32. And if you use a simple strength of material book, any of the standard book, and if you use the standard equation to calculate the deformation under the concentrated load for simply supported beam, you will find that this answer is correct answer. Okay, so this is the difference. If you choose the appropriate polynomial, then you are going to get the correct solution. So here you see, in the earlier case, even if you have used third degree polynomial, okay, because third degree, why I'm saying, because we have a3 into x to the power 3. So this was a third degree polynomial. Even if you are using third degree polynomial, still the deformation which you are getting at the center, it is not correct. So ideally it should be 32 millimeters. So in place of 32 millimeters, we are getting something like 24 millimeter. Okay, and if you remember, if you want to have more accuracy in the this polynomial function, and if you add one more term, that is a4 into x to the power 4, in that case your complexity of the problem will increase. If you remember, here we came across only one unknown. Okay, it was a1 and a2, and finally we have somehow established the relationship between a1 and a2. But if we add one more constant over here, so you will end up with a lot of calculations, and still it is not sure with all those calculations whether you will be getting 32 millimeters deformation at the center or not. But if you see, if you are using a trigonometric function, then only you can see within small efforts we have just solved this, and you will find very quickly the correct solution is found. Okay, so you need to understand one thing, that if you know the type of deformation, okay, whether it is sine curve or maybe it is a cos curve, if you use the appropriate function or appropriate displacement polynomial, then you can reduce your effort and you can even achieve the higher accuracy. Okay, so you have to choose it very wisely. If you don't choose this appropriately, your results are going to differ. Okay, so this is what I wanted to share today. With this, I'm discontinuing the class. So if you have any doubts, please remain in the